continue with the scheduling discussion. We studied the ASAP and ALAP schedules, and even though these apply to idealistic situations where you have infinite number of resources, between them they have some valuable information that could be used in a more realistic scheduling scenario. So, the information that we have here is that if you make the ALAP deadline the same as the ASAP critical path in terms of number of cycles, then the scheduling ranges that you come up with, scheduling range being defined as all the cycles, all the states between the ASAP and the ALAP where that particular operation can fit, give us an idea about the flexibility that the scheduler has with respect to that operation. So, we have these 4 nodes u, v, y and z having fixed schedules, which means that you do not really have any flexibility with respect to where to schedule them. For the others, there is some range and there is some associated flexibility. That is what comes out of the initial ASAP and ALAP schedules. This could be valuable input to some heuristic for performing scheduling. List scheduling is a standard heuristic for the resource constraint scheduling problem. So, let us study this algorithm in some detail. So, the idea is you assign some priorities to the nodes. Those priorities form a selection criterion among the different operations that are competing for the resources. So, the overall idea is very simple. You identify for each clock cycle or control step, these are used interchangeably. Control step is a little more general mechanism, but for now let us just treat them as the same. They become different when you have conditionals and there are branches in the finite state machine. So, you generate for each control step a ready list that consists of the set of operations, the set of nodes that are ready to be scheduled. When does a node become ready to be scheduled? When all its predecessors have already been scheduled. Either it has no predecessor or all its predecessors have been scheduled. So, that is when it is ready. So, you generate a ready list. If the size of the ready list is less than or equal to the number of resources that you have at your disposal, then there is no issue at all. You just schedule all of the elements in the ready list to that clock cycle or that control step. But if it is greater, then there is an issue. We have to decide which subset of the operations to schedule. That is what is difficult in the most general case. Although this is a local decision that is being taken, the impact is more global, the impact of the choice of the subset here. So, that is where this priority comes into the picture, and we try to schedule the operations with the highest priority. So, somehow the idea of a priority is associated with all the nodes, and you sort the nodes in order of their priorities and pick up the highest priority nodes for scheduling in that control step or clock cycle. In fact, that is what the idea of list scheduling is. Of course, you can see that the point of that algorithm really is the definition of that priority function. The algorithm is sort of a meta algorithm where the overall strategy is given, but the quality of the results that you expect is of course dependent on how good the priority function is. You could customize it based on what you expect. If there is any knowledge from the application or the particular graph or and so on, whatever is being scheduled, then that can be incorporated in some way. It can be very simple or it can be very sophisticated. The time that the scheduling algorithm will take would be dependent on what kind of priority function you use. If it is a very local priority function, it does not take into account too much of the dependent nodes and so on, then it could be very simple and efficient in terms of run time. But if it is a more complex one, then it would take more time. you can expect a correlation between how sophisticated this priority function is and the runtime of the scheduler. So, let us take a look at a popular priority function called mobility. That mobility is just defined for every node as the difference between the elapsed schedule and the ASAP schedule. It is a very intuitive priority function. For a node like S, you see that the ASAP schedule puts S into clock cycle 1, elapsed schedule puts it into the clock cycle 2. That is the range that we already identified this node has in terms of where it would be scheduled. So, the mobility is just computed as the difference. So, if the difference is 1, it means that there is some mobility. If the difference is 0, then there is no mobility, right. That is the cost function, and like we had seen earlier, we had defined this, we had determined these scheduling flexibilities, and based on that you can compute the mobility. It is the difference between these two numbers if you have an associated range. If you do not have a range, then that difference is 0, telling us that these are in some ways the highest operations. So, the node is on the critical path if the mobility is 0, and a lower mobility generally implies a higher priority. So, how is it useful in a practical scheduling algorithm? There is this information that is captured, which is if you delay a node which is on the critical path or which has low mobility, then that increases the probability of extending the schedule. So, let us just go through that algorithm with mobility as the priority function. This is the graph that we started off with. R equals 2 just tells me that there are 2 resources. Let us assume that all the nodes are of the same type. Okay. That is why I left out what they were actually doing, but each takes one cycle, and the 2 resources have to be used for determining a schedule for this graph. These numbers with the nodes are the mobility numbers. This is the priority function that is used by the scheduler. 0 means that all of these you do not really have a choice, mobility is 0. This, remember, comes about from the assumption that the elapsed schedule deadline is the same as the critical path that you obtained in the ASAP schedule. If you give a different deadline, then you will have a different mobility number. Remember, the elapsed schedule tends to get all shifted downwards, and therefore, a difference would be obtained between the ASAP and the elap schedule. This is a function of the deadline that you specify. But even though there is no deadline that is specified for the problem, remember this is a resource constrained scheduling problem, means that the resources are specified, deadline is not specified. The objective is to just arrive at the schedule that minimizes the critical path, that minimizes the length of the schedule. Still, we could use the deadline to compute an elap schedule in that obvious way. You just determine how many cycles the ASAP schedule took, and you give the same as the input to the elap. Okay. So, my ready list consists of these 4, right, these 2 and these 2, the 4 that are highlighted in green, and out of that I need to choose 2 because R equals 2. I have 2 resources of that type. Okay. So, this is where the priority function is of some use, because the number of ready elements is greater than the number of resources. I have to decide which 2 to take, and the choice here is that I will pick up A and B because they have the highest priority. Okay. So, A and B are picked up because the mobilities are 0, whereas the mobilities are 1 for the other 2 nodes that are ready. That leads to me dropping A, B from here. So, the ready list now consists of just C, D and E. C got free just now, so we add that into the ready list. D and E were already there in the ready list. Which ones do I select now? I can recompute the mobilities. Now that the decisions have already been taken for A and B, for the rest of the graph, ideally I would recompute the mobility. How would you recompute the mobilities? You have to run the SAP and LAP again. Now when you run, you can see that all the nodes are on the critical path. In this simple example, there is actually no flexibility. If you run ASAP, you would assign all three of them to the first clock cycle. To the second, you would assign these. ALAP is no different. So, either way you need 2 cycles, no matter how many resources you had, because of the nature of the dependencies here between the nodes. You can see that all the nodes are on some critical path or the other of length 2. That is why all the mobility computations result in the same number. So, all 3 of these are of the same priority for our mobility computation. So, this simple priority function does not distinguish further what happens if you get the same mobility for a number of nodes that is greater than the number of resources. Let us randomly pick 2 of them. You could make it more sophisticated. This is where there is some sub-optimality that is introduced in this simple priority function based algorithm. So, let us just pick up C and D for no particular reason, it is just a random subset out of the 3. So, if you schedule them into clock cycle 2, then that is what is left, and my ready list now consists of E and F. And what would I select from there for the third cycle? You do not have much choice, even though there is some flexibility for F. It seems as though G is higher priority than F, but because of the dependency on E, you are restricted to choosing F. You do not really have a choice here. We pick up F and E, that leaves G in the ready list, and you would select G. This time you have the number of elements in the ready list being smaller than the number of resources. So, there is no choice to be made. That is list scheduling. Using mobility as a priority function, you can see that you could replace mobility by something else, and you would still have what is called list scheduling. List scheduling refers to this overall scheduling mechanism where you do not revisit any decision once it is made. You make the scheduling decisions clock cycle by clock cycle, but you do not go back and change anything. This is very simple and efficient from a runtime point of view, but relying on the mobility cost function or mobility priority function means that we are not really guaranteeing anything about the quality of the result. This process will result in a fast, relatively fast scheduling, but says nothing about the optimality. You can't prove optimality of the resulting schedule. Where does the optimality question come in? Here you can see that there is one possible sub-optimality in this whole process, which is what is the subset of nodes to choose when you have a choice. That is a totally non-trivial strategy. You could come up with an example yourself where this random choice, well, it was not random, but it was random when the priority numbers were equal. But even that priority, there is nothing sacrosanct about the definition of the priority. It seems intuitive, it makes practical sense, but that does not lead to a theoretical guarantee of the best schedule. It is a good idea to think of counter examples that would defeat this strategy. For this simple example, it worked out in an obvious way, but sometimes the choice would actually depend on what is happening later. Here we did not look at successors of the node as we were taking this decision of which subset to choose. Of course, the successors were indirectly accounted for in some way by the priority function itself. The mobility computation, which resulted from ASAP and ALAP schedules, did take into account what is happening in the successive nodes. But this does not really make any guarantee, and the way to understand is if we can construct some examples where you do not necessarily get a good result. For this particular example, you can easily show that the result is optimal. What is the proof?
Why did we not take CD at the same time in the previous one? CD as the list and at the same time. Like the 0 was.
Why did we not take?
CD.
So, we had C, D and E as all being free, all being available in the ready list. Your question is?
Yes. So why did we not schedule at the same time CD? Like again we go to the E and Z in the next one.
We scheduled C and D at the same time. For the next time?
So
what's your question?
Why E for the next time? At the same time we can schedule.
Yeah, E could be in the second cycle.
You could have selected C and E instead.
C, D and E.
Oh, you can't because R equals 2. You have only 2 resources. So, you can only schedule 2 nodes per cycle. Of course, there is no intelligence that went into the choice of C and D. This was a random subset. I could have chosen C and E instead, or D and E. So, I did not a good priority function might actually anticipate the consequences of one subset or the other that is chosen. But what is the proof that you can't do any better than this?
Every clock cycle uses exactly the total number of resources available apart from the last time.
So we can
Right.
check depth of graph. So if depth of graph is 4, let's say 4, that is the minimum number of cycles I would need.
What is the depth of this graph?
So A
4.
Depth is same as
yeah.
height. What is the depth of this graph? Go back to the starting graph. This graph, what is the depth? 3. And schedule is giving you 4 cycles. But it is not hard to prove that you can't do any better than this. You should be able to derive the proof immediately. For this particular example, in the general case it is not clear, but for this you can show that you can't do any better.
So we have 7 nodes to process and we have 2 resources.
Yes, you have 7 nodes to process and there are only 2 resources. How many cycles will you take? 4 is the minimum number of cycles. So, yes, this is not a big proof. The dependency structures did not really matter too much because this proof is simple. But nevertheless, go back and come up with an example where this strategy is not good.
If I have unlimited number of resources, then that depth argument would hold, right? So if depth of my graph.
Oh yeah, that is what the ASAP schedule we came up with. That is a guaranteed optimal. You can easily show. If you find a path that is of length n, then you must require at least n cycles because of our assumption that each node requires 1 cycle, of course. Yeah. But the takeaway from here is that all the intelligence in list scheduling is in the construction of that priority function. This is a simple priority function that makes intuitive sense. It does not guarantee optimality. Here too, interestingly, there is some further engineering efficiency that is involved. Do you see any opportunity to improve this further while keeping the same logic?
Whatever critical path was given by the ASAP schedule,
Yeah.
we should not alter the priority in that path. Only alter priority of the other nodes or the tree in the graph when you recompute at second or subsequent iteration. Because if we would have, if we say
Mobilities are recomputed in our second iteration. What's your
the critical path.
So, we had CDE originally in the critical path. Sorry, yeah. We had okay, CF were there in the critical path. You are saying that we should not change the priorities. That is not clear. See, once you have taken, this is a constructive algorithm, this goes in the forward direction only. So, once you have scheduled A and B, there is no further decision, we are not going to reschedule it, although that is just a property of this algorithm. In fact, if you try to do rescheduling later on, you might find a better solution. But anyway, this strategy in the interest of time does not revisit the decision for a specific node. But under that constraint, you see that once you have taken the decision for some nodes, you might as well forget about those 2 nodes and drop them from the graph. And because of that, everything would change. Now, when you do SAP and LAP, a different set of nodes would fall in the critical path.
Sir, while selecting the nodes for computation, that time we take that into account that it should result into a computation. So if I have 4 nodes C, D, E, F, and I have to perform 2 addition, and if I C and D and E and F, if I choose C and E, it will not result into anything. So whatever the 2 nodes I am choosing, it should yield into a computation. That kind.
It should yield into a computation means. So I have C, D, E, F, and these C and D are involved in a computation in the next node.
Right.
So these are my choices. That's my ready list. And you are saying there should be that kind of.
And the same is with E and F.
Okay, if this is the case, then what should the choice be?
Then either I should choose C or D or E or F. I should not choose C and E.
Considering my R equals 2, it is better to choose either these 2 or these 2, but it is not worth the choosing one from here and one from there. Why?
Sir, it will not yield into any computation. So if I choose C and E, it will perform one operation in that cycle. But if I choose C and E, it is not performing anything. So okay. I have the equal.
Okay, so with R equals 2, let's shall we go and schedule this?
It should come out the same. At least in this example, the schedule comes out the same.
There is some merit in the argument. Unfortunately, it does not show up in this example because you have CD, you have EF, and you have GH, right? That is my schedule. If I had chosen CE as the first cycle, DF in the next,
Then GH.
you still get the same result.
If you have taken C and F in the first cycle.
If you had taken C and F.
In the first cycle.
Right, you took CE in the first cycle, DF in the next, GH. Yeah, here it does not show up, but this does bring up an important argument that I had alluded to earlier, which is all are not equal. They are equal according to some metric, that priority metric, but in fact with respect to their impact on later operations, they may be different. And as you can see, if you were to do a scheduling from here, if you had a lot of time, you could try all the different schedules, you could actually possibly choose the one that is best. But in general, even though it seems as though we ought to take the successors into account, a simple heuristic might not be there. What is often used is just this thing of height of the nodes going from the bottom. Here we did not, so this priority computation was the difference between ASAP and ALAP. You could take the height instead. This has some different implications, although both are intuitively similar. There is one issue that is there in this particular algorithm that we studied, which is after every cycle the mobilities are being recomputed, right. That is this strategy. There is some disadvantage with that. What is the disadvantage?
So the scheduler change between D and E was in the critical path earlier. That will result in more cycles.
Well, the algorithm is just, you are again computing the mobilities. So to perform that computation is not easy, it takes time. right. Even the LAP schedule, SAP schedule, you have to run SAP again, or you have to run LAP again and then compute all the differences. It seems as though it is an overkill to do this computation every cycle.
Once we have calculated the mobility, we can use some mathematical operation.
You have to somehow do some, while this is faithful to the idea of the mobility, it is computationally too expensive. You can do something about it. What can you do about it? One is you compute it once and then forget about it, and just use those numbers as you proceed with the scheduling.
I can't think of a counter example where this will not work or this can yield in a bad scheduling. But
Where
you just
the
choice one.
mobility,
Compute only once. I mean, I'm not able to think a counter example.
you are not able to think of a counter example online, but
Yes.
Offline, if you go back and think about it, you may be able to. The point is that we are making these random choices. Every cycle, when you make the random choice of the subset, you may actually end up with a situation where
All the nodes are equal in the sense they perform the same thing, it will not be a problem. But if the nodes are unequal, that means they perform different things and they have different delays, or then it starts making a
scheduling
difference.
is a difficult problem even under the simplistic assumptions that we have made. In the general, we will get to the generalizations. Remember, there are lots of simplifications we have made in this formalism. What are they? One is that there is only one operation type for this example, but what other assumptions we have made? Everything is falling into every delay is single clock cycle. So, lots of such assumptions we have made. The difficulty of the problem does not go away if you generalize it. That is why we are treating this simplistic version with some seriousness. But you could do several things. One is you could do that computation only once and just proceed. So, it leads to inaccuracies possibly later on, depending on what intermediate choices the intermediate choices were. Other is you could do that once in a few cycles, right, just in the interest of practicality. Instead of every cycle, you still can do the computation of the mobilities, but maybe once in 10 cycles, at least that helps improve the computational complexity. So, what we have here is a fully dynamic priority function, but it need not be completely dynamic. But that other example of using the height of a node, height being defined as the critical path seen from the bottom, right. This is actually an interesting alternative. It captures a similar property of the graph, but that is one that does not change as you take decisions about the schedules of the earlier nodes. Right, the height is a function of what happens later on in the dependent nodes. If you take some decisions about the predecessor nodes, scheduling decisions about the predecessor nodes, it makes no difference to the height. That is an alternative priority function that is that's popular. It's easy to see why it is essential. If the height is more, it means that the priority should be higher or lower. Priority should be higher because there are more, the list of the chain of dependent nodes is longer if the height is more. So, it seems as though we are capturing information that is not very different from what we did earlier, but this property does not change as you take scheduling decisions from the top down, because this is only dependent on what happens later on. That too does not guarantee optimality, but this is better from a computation point of view because you do not have to recompute.
Either of the two can be better in different cases.
Yes, you could also find other cases where height is not a good enough measure.
But the height we need to evaluate only once.
Yeah, but it is attractive from that point of view. As to which one is better, it is not clear, it depends on the properties of the graph. So, it is usually with experimental data that you say that this is performing better or the other one.
We have multiple destination nodes, so height from every destination node will be calculated, so that all the
Yeah, it's the maximum length from of any path from that node to yeah, that starts with that node. Right. Okay, let us refine this model by getting rid of some of the assumptions that we have made. First, of course, different operation types require different function units. The assumption in that first problem was that we assumed there is only one type of resource. So, all the nodes would be realized using that one resource type. But what if you had different operation types? You had additions, you also had multipliers. You still have the same graph as the input, but now you have different function units. How would you handle this in the scheduling algorithm?
So isn't it already handled in ASAP and ALAP schedule? So when we create ASAP or
The ASAP and ALAP schedule numbers are independent of what that function unit is doing, indeed. But what about later on as we do the list scheduling? So, you compute the mobilities, that is still common, that does not change, that is just a property of the graph, it is not dependent, it is a property of the dependencies and it is a property of the latencies of the nodes, but it is not a property or not a function of the type of node. So, that part remains the same, but what about the list scheduling?
So that part remains same, almost everything is same, unless we say it requires more delay or 2 cycles kind of resources.
Now we have
We will relax that also, but as of now we just have more types.
so we have different class of resources now. So
We have different classes of resources.
now
Right.
we need to choose that okay these set belongs to this resource and this set belongs to this resource and then do similar scheduling as we would do.
Right.
So
So,
it will be bounded by the number of function units also. That will be a
Yeah.
constant in our problem.
so what changes in our, so we had earlier some such graph where we identified that this was the ready list. So, there were only two things we were doing, identifying the ready list and from the ready list choose a subset to schedule, that is it, that is there in list scheduling, nothing else. So, if this is plus, if these are different resource types, then how does the strategy change?
So now we will see if we have the components which are used and we have that many resources.
Right. So, instead of saying r equals 2 earlier, I would have number of resources. So, plus, so this equal to maybe 2 and r star equals 1 or some such thing. This is saying that there are 2 adders and 1 multiplier. Right. So, that changes in the input itself, but here how does the ready list processing change?
The ready list will have two,
Yeah.
different
You
nodes will
have
different
yeah, so the ready list has a bunch of nodes that are of different types. You could think of it as a ready list for every yeah, operation type. Right. So, if this was A, this is B, this is C, then this would be A B and that would be C. You have different ready lists and you have these different resource types and the resource constraint is there on every individual resource type and you perform the same, the logic is the same, but it is applied to both the ready lists. For this ready list you are trying to select the best 2 nodes, for this ready list you are trying to select the best 1 node.
And both the ready lists are executed on the same clock cycle.
Yes.
Yeah.
The same clock.
Yeah, yeah. Of course, the ready list is independent of the clock period. Ready list just says that the predecessors have been scheduled, now they are there in the list. Which one you pick up now assigns those into a single clock cycle. But if you have different resource type, then in every clock cycle those resources can be used to do something and therefore, essentially it is like you are choosing from different ready lists and the different resource constraints would apply to the different lists. That is it, otherwise the algorithm does not change. There could be multi-function units. instead of assuming that every operation type, this is derived from the SDL, right, you wrote a plus or a minus or something like that, it translates to some resource type. Now, instead of assuming that each operation type requires a different resource type, we could have a more complex resource type that is capable of implementing more than one operation type. So, that could be the case if you have a lieu sort of operations where it is capable of doing plus and minus and logical operations and so on. Why is this interesting? It may lead to overall smaller area compared to if you had individual adders and subtractors and so on, right. So, I am just pointing this out, all of these generalizations we need not necessarily work out the details, but you can see that the algorithm does change if you have ALUs. Right. In what way would it change? Again, the ready list is the same as earlier, but now you could instead of saying that this ready list is specific to that operation type, earlier for the ready list, a different ready list maybe you would have maintained for the subtractor operation, but now you may actually combine them into a single ready list. It does get more complex when you have the ability to instantiate either an individual adder or a subtractor or an ALU. That is when the simple strategy is, you can't merely merge the two because you have a choice there that needs to be explored. So, it is not a trivial extension, but let us just understand that this particular extension is there to be explored in general. Okay, but let us look at a few refinements with respect to timing. We are trying to generalize that situation where this assumption where we said that all operations take a fixed amount of delay, okay, and that fixed amount of delay is 1 clock cycle. That leads to an inefficiency of the following kind. Of course, the different operation type in general take different amounts of time.
So now the precedence of operation will also come into picture if we are performing multiple operations together.
Precedence of the operations?
Like, sir, for example, if we have A plus B and in parenthesis and then C. So now we have to schedule accordingly. We cannot do B into
So
C
both
and
mass we
then.
need to take care of.
But that during graph formation we have already done, right?
Precedence of the operation, yeah, actually by the time you arrive at the graph, that has been taken care of. If you had A plus B minus C star D, what is a reasonable graph? Of course, it isn't as though there is only one graph that represents this, but the fact that this operation ought to occur, this has a higher precedence over this, is something that we did take into account when we formed the graph. The grammar of the language has been decided in that way, and therefore, the parse tree when it was constructed in the initial stages does have this kind of a structure that you have A, put the A B there. This kind of a structure you are assured that you are seeing at this stage. Right. Yeah. Where does this come? How did this happen? It happened through the grammar rules that we specified to the parser. So, of course, it has to recognize this in a way that is consistent with whatever our rules are. Okay. So, do you see this inefficiency? If I insist that I will schedule one operation in every clock cycle, then my clock cycle has to be as long as the longest operation that I have. Right. So, if the multiplier takes 20 nanosecond and the adder takes 10 nanosecond, then the clock, in order for any schedule to work, the clock period has to be at least 20 nanosecond, otherwise it does not work. And as a consequence, whenever you have an addition that is scheduled, all of that time is wasted. Right. So, essentially this leads to an underutilization of those fuse that are simpler and faster. In fact, those might be more in number Those nodes might be more in number, add nodes might be more in number than the multiplier nodes, and because of this inefficiency you might end up wasting a large part of the schedule. Okay, what can we do about this? Yeah, so we have to relax that assumption that all of these operations, even if they were combinational, we have to relax the assumption that they all finish in one clock cycle. Let us define the delays to be independent of the clock period, of course. Who decided what the clock period was? If for this algorithm, the clock period was an input. Who decided what the delays of these function units were?
Structure of the
Adder delay and the multiplier delay. Who made the decision?
that's when we designed it.
The library designer designed cells and all of these components, and this decision was an outcome of whatever the design steps were in designing those components. There is no relation between the two. Library came from somewhere, and the application requirement might require us to run it at 1 gigahertz or something like that. There is no relationship between the two. So, in general, let us just relax that assumption that the delays have nothing to do with the clock period. So, if they have nothing to do, if the clock period were 20 nanoseconds or greater, then we are okay, we don't, nothing changes. But what if it was less? If it was 10 say, then the add would finish in one clock cycle, but the multiplier would take multiple clock cycles. But in general, the number of cycles for a function unit can be computed like this, whatever is the characterized delay of that component divided by the clock period. You have to take the ceiling of that to give you integral number of cycles. That is the treatment as far as the schedule is concerned. There is one implication with respect to the controller. What is that implication? Scheduling, it is very clear. Earlier we used to put every node in one clock cycle. Now I have to stretch the schedule for a node to multiple clock cycles, right. So, that part is quite clear, right. Multiple clock cycles. But there is one other thing that is implied from the design's implementation point of view. When you have a multi-cycle operation, multi-cycle combinational operation, what do you need to ensure?
Output from that resource should not be used before it is.
Indeed, the meaning of the multi-cycle operation is that the output is not ready at the end of the first clock cycle, it is ready at the end of the second clock cycle. I should rely on its value only after the second clock cycle, which is fine, right, because if there is a dependent operation to this multiplier coming later, then that would be scheduled into the third clock cycle onwards. That is all right, that is not hard to implement. There is just one other thing you have to make sure.
The output of, in this example, the output of adder
Yeah.
has to be retained like a no-op or a pipeline somewhere in between that. It should be carried on to the next, some register inference or
actually
some
this,
pipeline has to.
the output of the adder can be used in the second clock cycle, remember. If you wanted to, you could use it. If you do not use it, instead if you use it in the third cycle, what is the, how do you realize that? Store, yeah, we did say that the moment there is an edge, dependency edge that is crossing a clock cycle boundary, you have to store it in a register. That we already know, but what is different now for multi-cycle operations? The inputs to the operation, they have to be held stable for multiple cycles. Right. This is an obvious requirement. Since this is taking multiple cycles, of course, the processing is incomplete at the end of the first cycle, you need multiple cycles. So, which means that if they came from a register, then that register cannot be reused for the duration of this operation.
And if they are coming directly, then they need to be stored in the register.
If
They are coming directly from another operation.
if they came directly from some other operation, then you did, this falls into the standard requirement that I have an edge, a dependent incoming edge which crossed a clock cycle boundary, right. This previous clock cycle boundary is what it crossed. Therefore, you need a register for it.
How do we capture this timing requirement in a graph?
Till now we were capturing everything, the dependencies in form of a graph, right?
Right.
But now I have two dependencies. One is I should not use the output before it is processed, I should keep my input stable
till the output is there.
output is there. So this is a kind of timing dependency onto my operation. So how do I capture this in graph?
In the original graph you do not capture it. Original graph was capturing only the functionality. That does not change. This needs to be maintained through the later phase of the scheduling. So, this is an implication that comes up later. Right now it is okay, the scheduler only sees the nodes, the resources have delays associated with it. Right. So, in fact, an individual node which you say plus or a star might actually be implemented in many different resources, maybe it is an ALU, maybe it is an adder and so on, each of which would have a different delay. So, that delay is to be taken into consideration as you schedule the nodes. The scheduler does need to be aware of it, but more important, later on these decisions have to be communicated somehow when register allocation is being done, so that you do not rewrite the register at the wrong time. So, some information has to be handed over from one stage of the synthesis to the other. The input representation does not change, it is still the same.
Basically, if I understand correctly, this information is annotated in the system and it's
Somewhere, yeah, it's some data structure that we are not talking about yet.
But it's scheduler's responsibility
To take care that before it is done, then only schedule the next thing on this function.
Scheduler's responsibility is only to make sure that a dependent node of a multi-cycle operation does not get scheduled at the wrong time, does not get scheduled too early. So, anyway, instead of me saying, why do not you suggest how to extend the scheduling algorithm? It is a formal question that is posed to you in the slide. How do I modify list scheduling to take care of this?
While building the ready list, at least one thing we can do is, we can't say the dependent nodes are ready for the multi-cycle output.
Yes.
Right. That much we can figure out automatically without much effort.
So, this is a change in the ready list computation. Yeah. So, check not merely whether the predecessor has been scheduled, because it might have been scheduled and might not have completed. Right. So, you have to check that enough cycles have passed that all predecessors have completed their operation, that is all. Once you do that, once you put it into the ready list, the rest does not change. What about the idea of the height and the mobility and so on? What happens to that when you have multiple multi-cycle operations? You have, let me assume that this delay is 2 and this delay is 1, and you have some such. ASAP and LAP computations have to change now. In what way will they change? So, these are going in this direction. What goes into the first cycle in the ASAP? A, B, C, D. A and B clearly are scheduled into the first cycle, so that is okay. B has not completed yet, and what is ready now? So, C cannot be scheduled yet, right? Even in the ASAP, forget about resource constraint, but even in ASAP it can't be scheduled because of the dependency on that multi-cycle operation. After this I schedule C, and after this I schedule D. So, ASAP ALAP computations change in this simple way, that your calculation will not merely do +1. Earlier our algorithm was that the schedule for a particular node was computed by adding 1 to the max schedule of all its predecessors. That was the equation. Here I would change it in an obvious way. I would not merely say max +1, but instead it would be
the size of the node. Max
each has a latency. So, sigma of a node was when it is scheduled, and let me add a latency of a node in that way, and this schedule for a dependent node would be in terms of. So, earlier we had 1 plus max schedule of u, where u was in pred of n. This is what it was. Instead, it would be now what? It would be 1 plus. So, u belongs to so over all that max was over all the u.
Max of u is ln minus 1.
ln of max of delta
Sigma.
Would I still have max of
ln of max of
sigma u plus L u?
no, then I have to do -1
Minus 1.
because I am consuming max.
Let us define this as okay. So yeah, let's remove this. L is 1 if it's a single cycle operation. Okay. So is this okay? Where u is over all the predecessors of the nodes. So it's a simple computation. This is still optimal. The ASAP schedule is still guaranteed to be optimal. ELAP schedule similarly you can obtain.
Now let's say my scheduler was considering height in its
Algorithm.
Yeah.
Then height will be now height plus these depths. So
Same thing.
Yeah, it would be in
L.
terms of cycles.
L.
Yeah, it would be in term computed in. That's an easy computation, but it would be a computation in terms of cycles, which is the sum over all the individual cycles of multi-cycle operations, if there are any. Okay, so that's one generalization. Not much changes, as you can see in the overall strategy of the scheduling. Height is still an important priority function. Mobility is also a relevant priority function. It's just that the way you would compute them would be different. How about generalizing in the other direction, where clock cycle is given and the FU delays are too small, not too large compared to the clock cycle, but too small compared to the clock cycle. So small that in fact dependent operations could be scheduled into the same clock cycle. Right. This is an example of that. I have dependent operations, and the standard algorithm we have seen so far would actually put them in different clock cycles just because they are dependent. But actually if you look at this, you see that there is enough time to schedule both of them in the same clock cycle. That would lead to better utilization of resources. It has some implication though. So ideally I would like this, which is why not, since I have enough time I should schedule both of them dependent operations also into the same clock cycle as long as enough time is there. This has one implication with respect to resources. What's that?
The resources have to increase now.
You need two adders to do this. This is a combinational operation still, right? It's a combinational circuit. So chaining can be done if you actually have more resources. You could still have muxes between them in this path, in the sense that in some other cycle you could be reusing that adder to do something else, you could be reusing this adder to do something else. But still for this to work, you could have muxes, but you shouldn't have a register in between them. So one path should be there from the output of one adder into the input of another adder. So that's what is called chaining. Multiple FUs are required, but if there is enough time, then you should be able to accommodate dependent operations into the same cycle. How do you change the scheduler for this?
So now we look at the downstream nodes also for the dependency. We can't live with the current method as is, because we don't know if a register was needed in between.
But remember, at the scheduling time, we don't worry about registers. Registers are inferred, but that happens at a later stage. Right? We don't have to worry about whether we have put a register already or not. This solution being that if we decide to chain, then we will create a path later on between the output of one adder and the input, whatever the mux was there at the input, we will introduce that path. So register decisions have not yet been taken, but that's all right. That does not really affect this.
An example, sorry.
Sir, initially, like in that algorithm,
Yeah.
we were when we had a bigger functional unit, we were giving it a value of 2. Going by the same analogy, we can give this as half
Partial.
clock cycle, and the height algorithm from downwards would work as the same.
The height, if it was defined in terms of number of cycles, then that is an integer, and it does change.
So now we can give these blocks as a height of half, and then when we compute the height. No, but
The height could be an absolute value as opposed to relative value.
No, instead of an integer values, we give them a real value. So we allow a continuous domain.
Yeah. So of course the delay is a real number. It need not be an integer. Delay need not translate to a fixed, an integral number of clock cycles. You could, as part of the height computation, just you could define the height in terms of actual delays instead of cycles. You could do that. Ultimately, the scheduling decision does translate to integers, though. What circuit does this translate to? That schedule that we have. Sorry. Right? This translates to what circuit? Then what?
Then another adder.
I have another adder.
Then register.
That's it. Yeah. As of now, that's just that you have. So when is this second adder looking at its input?
we are sampling the output only after cycle, and that's fine for us.
This is a combinational circuit. It is looking at its input all the time, but the point of the schedule is just to make sure that by the end of the clock cycle, we have the right value on the output. It is giving us incorrect results somewhere in the middle of the clock cycle, but that is okay. Okay, now handling this does require changes at multiple stages. The priority function could change, but even before that, there is a simple change that we have to do that is not dependent on what is happening later, but when you have the ready list, you are already checking whether all its predecessors have been scheduled first. Later on, we extended that to say whether all its predecessors have been scheduled and they have completed. The third check that you can make is whether it is possible to accommodate this, considering where all its predecessors have been scheduled. Let us say I have a node here, it might have one predecessor here, might have some other predecessor there. Considering the different clock cycles in which this node's predecessors have been scheduled already, could I move it to an earlier cycle than the current one that is being considered? So that is all that is there. Now, you could refine the priority computation and so on, of course, to make this. Yeah.
In this case, what will happen is we'll go back in time and then add the second add operation there, right?
Yeah.
Yes. So we are altering our so far whatever scheduling we are doing, we are not looking back in our previous cycles, but now in this case we'll go back in our previous cycle and then create.
So let us tweak the since we are violating something, let us tweak what it is that we were not supposed to violate. We will not revisit the scheduling decisions for a node. Looked at it that way, we are still not revisiting anything. We are changing what is happening in each cycle because we changed the decision for that clock cycle. But
Two adders become a single node in this.
no, it is still no. That's still two different nodes.
There's still a graph. There's still an.
It's still a graph, so nothing has changed. But because you would have other dependencies, perhaps, right, from here to others. So that the graph structure is still maintained. There is no merging. At least this does not require the merging. We did do some merging in one of our transformations. Remember when we had that MAC operation, we actually substituted multiple nodes into one node. This isn't an example of that. This is a proper chaining in which you are instancing both the resources and are connecting up in a way that both are being scheduled into the same clock cycle, but otherwise there is nothing complicated that is happening. Let us look at the other problem definition. We looked at resource constraint scheduling. Resource constraint scheduling fixed the resources that you would take, and the optimization was to minimize the latency. Time constraint scheduling is the other way around. You impose a latency constraint, that is a deadline, that says that you must schedule the DFG within a fixed number of cycles. But within that you have the flexibility to schedule operations wherever you can, and in the process you optimize the resources, right. So, in general this is a time constraint for the entire DFG, but you could actually extend that to also mean a time constraint between particular nodes of the DFG. When that happens we will get to, but in any case you have time constraints. Those could be of different types. It could be a max time constraint, that is what we normally understand by a deadline, but it could also be that there is a min time constraint. It could also be that there is an exact time constraint. When you say 5 cycles, it should take exactly 5 cycles. Such extensions one can also think of. Those are also practical in some scenarios. Okay. So, that is the constraint, but what we optimize then are the resources. It is an area optimization. Timing is fixed and you have to perform area optimization, and that means in terms of resources that you try to minimize the number of resources that are required to implement the DFG. The classical time constraint scheduling algorithm in high level synthesis is called force directed scheduling. This too is of the kind that the basic idea is simple, but that could be extended in various directions. Hardware is minimized subject to a time constraint. The idea is you try to uniformly distribute operations of the same type across control steps. So, the intuition being that suppose you had 4 operations to be performed, right. So, those could be distributed like this, those could be distributed like this, could also be distributed like that. Which one would be preferred? Third one would be preferred. Why? Minimum clock cycle, but that is not our problem here. Problem is a deadline is given to us, and for that deadline we have to arrive at a minimum resource schedule.
Then the first one, if the deadline is 4 o'clock,
Yeah, the answer is it's an incomplete question because I didn't tell you what the deadline is. If I don't tell you the deadline, how can you give me the minimum resource? So, if the deadline is let's say it is 4, then
Minimum deadline is 4 or?
no deadline. If I didn't say anything else, then let us take that it is a max deadline. You must complete the operation within so many cycles. So, let us say it is 4, yeah, it could be exact also. Remember that exact and minimum you could actually translate one solution to the other. So, in any case, suppose I had 5 operations. Of course, you could add a dummy state and nothing changes, right. If it has to be exact, you could still add one more clock cycle and nothing changes. Okay. So, if I said 4 was the deadline, then you would go for this, you would not go for this. Why?
only one resource is
Because of a single resource. If I said 4 was the deadline, but I had that kind of let us say I had 5 operations, then would I go for, so I have to do something like that, or I also maybe can do something like that. I also have 5 operations. Pardon me?
How many resources have you have?
We have to.
2 or 3.
You have to tell me how many resources. You have to optimize the number of resources. Remember, the resources are not fixed. I am only saying that 4 is the deadline. This one would be chosen because you require fewer resources. So, what about this?
In the first one, why I took 4?
My deadline was 4, so that
4 is the maximum, right?
yeah.
So I rather schedule the last one with third one. I have 2 resources.
So we can complete in 5 cycles.
No.
We can complete in 3 cycles.
You can, but okay, it doesn't help to complete faster. The point of resource of time constraint scheduling is that the time is given. If you don't use that much time, then it's your problem. You are not saving anything by.
So that depends if it's maximum deadline or minimum deadline.
Yeah, so I already said it's max.
There may be some dependencies also. We can't do like that exactly like 1 1 1. So in the second we can do like 2 headers at the same time, and the third one also 2 headers at the same time. So there may be some dependencies also.
Some dependencies might be there. This is, if drawing it this way, I mean that there are no dependencies, but of course your solution is based on what dependencies are there.
Question actually. If I choose all sequential, let's take the first question. One resource schedule in one cycle, that has an impact on the size of control FSM size. Now,
FSM size.
yes. So
In what
is
way?
it always trivial in practical life that the decision on the size of FSM is not always critical? I mean, it doesn't become a determining
FSM size
factor.
can make a difference. Here, so let's say I have one resource, right? On all these 3 cases, I have a single resource each. So which means that that's my resource, and there is a mux here for which the select input is coming from the FSM. Well, actually, for this solution, you would have 2 different adders with muxes, maybe in the general case. Actually, the second one does not require a mux, but the first one does require a mux. So I think your point is that this one might have a 4 input mux.
And plus the registers that I need to.
This one might have a 3 input mux, because the other one there is no select that's there. Yeah, that's an interesting complication which sometimes we don't really address properly at the scheduling stage, because we are not at that level of abstraction yet. But we could. The extent of sharing that is implied by one solution versus another solution could actually be incorporated in some way in the scheduling algorithm itself. So, in the interest of simplification, we are doing these steps in sequence. We are doing scheduling first, and then we are doing resource binding, and then we are doing register allocation. But what these are pointing out is that these are interdependent, the decisions are interdependent. What decision you take here might actually make a difference later on. Right.
So do these decisions also take power into account?
So for example, let's say I have deadline headroom. Okay, I can take 4 or 5 cycles.
Yeah.
Then I need not to power up my another functional unit, though it is available, but I'll save on power by just.
Yeah, as of now, these formalisms we have not taken power into consideration, but indeed power would be a reason to prefer this kind of a solution to this kind of a solution. At least peak power would be better in this solution than in this solution. Of course, area point of view, this one requires more resources than this, then therefore you would choose this.
Will be better in first one.
See, if our deadline was 4, then you could say that the average power does not change, because that's the energy of 5 operations, it's divided over that much time. Yeah, if nothing else is happening, if you have no op states, no other operation is scheduled, then indeed the total energy is the same, therefore average energy is the same. But from a peak power point of view, you would choose that. But the intuition that maybe we can stop at for handling time constraint scheduling is that you try to uniformly spread out the resources over the clock cycle. The more uniform it is, the more likely it is that you have fewer resources. It is better utilization of the resources, right. If the usage is skewed in this way or in this way, then you need more resources. Power also presents an interesting application of the same idea. Peak power at least does. You have a better solution if you uniformly spread out rather than if you bunch operations together. And force directed scheduling formalizes this idea in some way. Maybe let us stop here and introduce the actual force directed scheduling in the next lecture.